Good morning, dear student. In today's lecture, we are very much interested in the important topic uh, of our course CH290 organometallic chemistry, that is the number of iron bands. So, we are discussing the number of iron bands for the carbonyl complexes because the carbonyl is a very famous ligand for in this organometallic chemistry. So we considering the mononuclear carbonyl, dinuclear carbonyl, and then if you consider the complex containing three or more carbonyl. So how one can find out the number of iron bands and what information we get from this number of iron bands. Okay, so we will discussing in this lecture. This is very important point regarding your CSR NET and SET exam, because many times the question is asked that how much iron band are possible in this complex carbonyl complex. Okay, so in this case we discussing the carbonyl complex to find out the number of iron bands. Before discussing the number of iron bands, you should keep in mind that the important point is that higher the symmetry. So in many cases, the number of iron bands can be find out with the help of symmetry. So higher symmetry. If the complex having higher symmetry, then it have lower IR bands, and the complex having lower symmetry, then it have a higher IR bands. So you should keep in mind. So this point we discuss later on, but at least you should keep in mind whenever there is a higher symmetry, means the molecules or the complex having tetrahedral, octahedral symmetry, or the point group may be DNH, then it in that case there is a lower iron bands, while the lower symmetry complex will shows higher iron bands. So let us discuss one by one. Let us discussing the number of iron bands for the mononuclear carbonyl complexes. The first one, that is your mononuclear mononuclear carbonyl complexes. Mononuclear carbonyl complexes. So mononuclear carbonyl complexes means what? There is only one carbonyl, and the complex has a single possible carbon stretching mode. So mononuclear carbonyl means what? This metal, it is attached to this carbonyl, and if you consider in this case, we get only one iron bands, only one iron bands. Okay, so whenever we considering the mononuclear carbonyl, okay, only one carbonyl is attached to the metal atom. In that case we get only one iron bands. Okay, and we know that this carbonyl is your terminal carbonyl is there, and we know that for terminal carbonyl we get the lambda, not lambda x, we get the iron bands at 2120 to 1850 per centimeter. So this is the carbon stretching frequency, or we get the iron bands in this region for this terminal carbonyl complexes. So mononuclear complexes, the complex having single possible carbonyl stretching bands, in the IR spectrum. Okay, so we get a single IR bands for this mononuclear carbonyl, because whatever the carbonyl which is attached, it is a terminal carbonyl, and we get only one IR bands. Let us discussing the second one, that is dinuclear carbonyl complexes. Second, that is dinuclear, or we can consider dicarbonyl. It is not dinuclear, dicarbonyl complexes. First, we discussing the monocarbonyl complexes. Second, that is dicarbonyl complexes. Means there is a two carbonyl ligands which is attached to the metal atom, and in this case there should be two possible geometries. That is, whenever two carbonyl is attached to the metal atom, one is your linear geometry is there. Okay, linear geometry is there, and the second one, this is your linear geometry. Okay, and the second one, that is your bend geometry. This metal, it is attached to this carbonyl, metal is attached to this carbonyl. So this is the two geometry for dicarbonyl complexes. And how many iron band is possible in this linear and bend geometry, so we will discuss in this dinuclear complexes. If we consider the basic principle of IR active molecule is that whatever the complex or molecule it will shows a dipole moment when there is a symmetric stretching and antisymmetric stretching, symmetric or symmetric stretch. So if you consider this carbonyl molecule or the dicarbonyl complexes, one is linear, one geometry is linear, another is bend. So in this case, in linear case, we get only one IR band. We get only one IR bands in IR spectroscopy. Okay, only one IR bands in this for this linear geometry, and we get two IR bands, in bend geometry. So how one can prove that the linear molecule undergo only one IR bands? Okay, the linear molecules having only one IR bands and the bend geometry having two IR bands. If you consider this linear molecule, that is when there is a symmetric stretching. So in this case, if you consider when we were considering the symmetric stretching, okay, let us discussing why we get only one IR band in this linear geometry and why we get two IR bands in this bend geometry. So if you consider the first one, that is your metal, this is your carbonyl, okay, this is your carbonyl, and when there is a symmetric stretching, okay, if you consider there is a symmetric stretching, and we know that the oxygen is more electronegative as compared to carbon, and if the bond get stretched, and this is a symmetric stretching. So if you consider this is your symmetric stretching, both this CO bond get stretched in symmetric manner. Symmetric stretching, we can consider it is not symmetric bond, it is symmetric stretching, and due to the symmetric stretching, the net dipole moment, okay, the net dipole moment, it becomes zero. So there is a no change in dipole moment. So okay, if we consider whatever the bond get stretched in this side, same is the bond, same distance, or we can consider same length that this another carbonyl also get stretched. Okay, and therefore the no change in dipole moment or the net dipole moment is zero, because this is a symmetric stretch from both the side. If you consider the left hand side and right hand side, there is a symmetric stretching of this carbon oxygen bond, and therefore no change in dipole moment, no change in dipole moment, no change in dipole moment, and therefore it is IR inactive. IR inactive, so it is IR inactive, so it does not shows any IR bands it does not shows IR any IR bands because it is IR inactive. That is, whatever the symmetric stretching of this linear geometry, it is inactive, and therefore we does not get any bands in this case. But if you consider uh, this asymmetric stretching for this linear geometry, that is, this is oxygen. Okay, this is the oxygen, and if you consider the antisymmetric stretching, means in this case, if you consider this is symmetric stretching and this is your antisymmetric stretching, so one bond get stretched. Okay, I will draw it. This is metal, this is carbon, this is oxygen, this is oxygen, this is your carbon, and this is your oxygen. Okay, so if you consider this bond, this carbon oxygen bond get stretched, then this oxygen carbon bond. Okay, so this is we considering is as an antisymmetric stretch, that this bond is also stretch in this direction, and this bond is also stretch in this direction. Okay, and therefore this is called antisymmetric stretching. So in this case, the stretching is symmetric, that is, both the bond get stretched in symmetric manner. But in this case, this is your antisymmetric stretching, that is, the direction is same, so whatever the stretching is occur in the same direction. Okay, the magnitude is same. Okay, we can consider the magnitude, not magnitude, the direction is same. In this case, the direction, that is, whatever the stretching, the direction is same. In this case, the direction is different, therefore the overall change in dipole moment is zero in the symmetric stretching. While in antisymmetric stretching, antisymmetric stretching so this is your antisymmetric stretching, means if we consider the antisymmetric stretching, that both the stretching having the same direction, it is not in opposite direction, and therefore there is a change in dipole moment, because one bond is stretched and one bond get compressed. Okay, one bond get stretched and another bond get compressed, so change in dipole moment, and therefore we get IR, and this molecule is IR active. This molecule is IR active, and we get one IR band for this antisymmetric stretch. So for symmetric stretching, the molecule is IR inactive, and it does not get any IR bands for this symmetric stretching. If you consider the antisymmetric stretching, there is a change in dipole moment, it is IR active, and we get only one band. Okay, for this antisymmetric stretch. Okay, so we get one band for this antisymmetric stretch. Let us discussing the second one, that is your second, that is bent. Okay, bent geometry is there, that is bent geometry is there, and this is carbon, this is oxygen, this is your carbon, this is your oxygen. You can consider here, this is your metal, carbon, oxygen, this is your carbon, oxygen. Okay, this is your symmetric stretching, and it is also IR active because it is a bent geometry, it is IR active. Okay, it is IR active and it is symmetric stretching, so which results into the change in dipole moment, therefore it is IR active. And similarly, if you consider the second, that is MCO, another is antisymmetric. So this is antisymmetrics. So here also the change in dipole moment, it is antisymmetric or asymmetric we can consider, and it is also IR active. So in this case we get two IR bands due to symmetric stretching as well as asymmetric stretching. But in linear geometry, the symmetric stretching is IR inactive, and therefore we get only one IR band due to the antisymmetric stretching. While in bent geometry, both the stretching, that is symmetric stretching as well as antisymmetric stretching, are IR active, and we get two IR band in this case. Okay, and therefore this IR spectrum can be a convenient tool to determine the structure for molecules, okay, to have exactly two carbonyl ligands. So whenever there is a two carbonyl ligands, this IR spectroscopy, it is very useful, indicating the carbonyl is a same carbonyl or a different carbonyl. Carbonyl is same carbonyl or different carbonyl. So we already discussed that a single band, whenever there is a so you should keep in mind, whenever we get a single band, whenever we get a one band or single band in IR spectrum for dicarbonyl complexes, the geometry is linear geometry. So you should keep in mind whatever we discuss. The conclusion is that whenever we get one band in IR spectrum for dicarbonyl complexes, means it containing two carbonyl ligand, dicarbonyl complexes, the geometry is linear, and we get, when we get two bands, okay, when we get two bands in IR spectrum for dicarbonyl complexes, because we discussing the dicarbonyl complexes, that is one geometry is linear, another geometry is bent. Okay, the conclusion is that when we get one band in IR spectrum, the geometry is linear. Okay, the geometry is linear. And the second when we get two bands in IR spectrum, the geometry is bent, because we get two IR bands for bent geometry, because both symmetric as well as asymmetric stretchings are IR active. But in linear, the symmetric stretching is IR inactive, only we get one IR band due to the antisymmetric stretch. So this is all about the dicarbonyl complexes. If you consider the complexes containing three or more carbonyl, okay, if you consider the complexes containing three or more carbonyl, then we can take the help of the point groups. Okay, again we consider the symmetry. So we already discussed that higher the symmetry, so we considering here more than three or the complex containing three or more carbonyl. So okay, so we considering here, we already discussed the monocarbonyl, dicarbonyl, and the third one, that is the complex containing three or more carbonyl. So how one can find out the number of IR bands in this case, that is complex containing three or more carbonyl? Again we take the helps of the symmetry, that is your point group. And we know that we already discussed the first important point is that higher symmetry of a complex having lower IR bands. So you should keep in mind the first point, higher symmetry means the molecule is tetrahedral, octahedral, then there is only one IR bands, because all carbonyls are equivalent. Second, the lower symmetry having higher IR bands. Okay, the third one, that is you should keep in mind, when the point group is tetrahedral, octahedral, okay, having higher symmetry. Point group is tetrahedral, octahedral, or D and H, then in that case we get only one IR band. We get only one IR bands. Okay. Second, if the point group is C2V or CS, then we get the IR bands, which is equal to the number of carbonyls. Okay, so number of carbonyl, which is equal to number of IR bands. Number of carbonyls, which is equal to number of IR band for the point group of complex is, if the point group of the complex is C2V or CS. So whatever the carbonyl is there, we get the number of IR band. If there is a 3 carbonyl, then we get 3 IR bands. If there is a 2 carbonyl, we get 2 IR band. If there is a 4 carbonyl, then we get 4 IR band. The next important point is that if the point group is C3V, if the point group is C3V, okay, any carbonyl complex having the point group is C3V, then the number of IR bands, which is equal to n minus 1. So what is n? N is nothing but the number of carbonyl in the complex. Number of carbonyl in the complex. So you should keep in mind, for tetrahedral, octahedral, we get only one IR band. For C2VCS, the number of IR bands, which is equal to the number of carbonyl. If the point group is C3V, then we get number of IR bands, that is n minus 1. That is, what is n? The number of carbonyl in the complex is n minus 1. If it is 4 carbonyl, then 4 minus 1, so we get 3 IR band. If there is a 3 carbonyl, then 3 minus 1, so we get 2 IR bands for the point group is, if the point group is C3V. The next important point is that if the point group is C4V, then the number of IR bands, which is equal to n minus 2. So again, n is your number of carbonyl minus 2. So you should keep in mind, okay, the point group, that is whenever C2VCS is there, the number of IR band is equal to number of carbonyl. For C3V, n minus 1. For C4V, n minus 2. For tetrahedral, octahedral, and DNH point group, higher symmetry, lower IR bands. Lower symmetry, higher IR bands. Okay, so this is all about the IR bands. Okay, so you have to find out, in the next lecture we're discussing certain geometries and the number of IR bands with the help of this point group and the remaining points of this first chapter. Okay, thank you.